maybe also 6 minutes.
Sorry?
No problem. Okay.
Or we can stretch a bit, you said, sorry?
Yes.
Okay, great. Yeah, I agree. We can be we can stretch a bit, but at the same time I think it's important to preserve time for the conversations later, because that's, I think, what the presenters too are gonna be valuing, okay? So we're ready to start. Okay. So Stefano, do you want to start sharing?
Yeah, sure. So as a feedback from this morning session, actually, if I'm not mistaken, we finished with 20 minutes early or 50 minutes early. So I don't think there will be need to rush.
Okay,
But
great.
anyway, let's keep for the 5 minutes.
Make,
Okay.
makes sense. Makes sense. It's no problem for me if it's okay for you, but I'd like to. Okay, so we can let you know when you ran your five
Yeah,
minutes,
sure.
and we can check if you need some more time. Okay.
Okay, thank you. So if you confirm that you can see my presentation, I will start.
Yes, we can. At least I can.
Hopefully, internet will be steady because here there is a kind of storm. So,
Oh,
yeah. So, welcome everybody. So today I'm here to present this paper that we submitted together with my colleagues Fabio Falumba from University of Salerno and Dario Dinucci and Damian Zamburi from Eindhoven and Tilburg University. That we submitted to Transactional Software Engineering and was accepted in January 2021. And it is about the within project defect prediction, but on infrastructure as code rather than on traditional application code. So the goal of this work was to propose a prediction model for failure-prone infrastructure as code scripts that could be useful in practice, but also to investigate the roles of product and process metrics. And with product metrics, I mean the infrastructure as code specific metrics. Also to understand which of those metrics and which model should be used to create a framework that could be used in practice. Why we decide to do this study for infrastructure as code? As you may know, infrastructure as code, which is machine-readable configuration code that can be used to manage and provision cloud application, has several advantages with respect to manual provisioning and manual configuration of infrastructures. For example, it ensures efficient and repeatable management and provisioning. At the same time, it improves consistency and reduces also the time, effort, and specialized skills to provision and scale infrastructure. Think about that; it can also be used through system versioning control system, for example. But there is a drawback. I mean, it is still code, so that means that it's still affected by similar errors to those one in application code. For example, here we have a code written in Ansible, and you can see this was taken from a real world project, an issue. There was a bug in a condition at line 15 highlighted in red that says do that operation when the variable is virtual and is not defined, which was wrong. And the fix, as you can see in green, is that variable should be compared to an empty string and as well to known. So you can see that here, from a concept point of view, the error might be similar, but infrastructure as code requires different constructs. So we have to identify those problems in a different manner and define other metrics, other measures to identify those kind of bugs. The goal of this project was to create this large empirical study and to evaluate the classification techniques, machine learning classification techniques, and feature that our framework could rely on to achieve the highest detection accuracy. We collected 104 real-world Ansible-based projects and a total of approximately 5,000 defect fixing commits and 4,500 defect introducing commits using this SZZ algorithm. And for a total of more than 700K snapshot of failure-prone and neutral files. We used 5 different common used classifier models: naive-based, logistic regression, decision tree, random forest, and SVM. We evaluated the performance using different measures like precision recall, F measure, and so on and so forth. But we focused on the out precision recall because the problem was highly imbalanced. and the metric correlation coefficient. So we focused mainly on those and reported those measures, although the others are available online. And we used I worked forward validation techniques to select the best model, because we are in a context or within project defect prediction. So for every release, we train on the first release and test on the second one. Then the next step, we train on the first two release and train on the third one, and so on and so forth. So we had 3 research questions. The first one was about understanding the impact of learning techniques. So to what extent the classifier selection impacted the performance of the models to identify those failure-prone scripts. So this was the design. We get the 100 for Ansible projects. We ran the models on all of them, and we performed the with context rank and ConsD to evaluate the difference in their performance and the effect size. So here you can have an overview of the performance, and we observe random forest to be the best performing model with an AUC PR of 0.93 and MCC around 8.8. So we can say that random forest performs statistically better than the other one that we analyzed with a large effect size. The second research questions was about understanding the impact of the metrics selection on the performance, so not anymore on the of the model selection, but on the metrics. So we took the best model, the random forest, from the previous research questions, but this time we train it with different sets of metrics. ICO here is the infrastructure as code oriented metrics, like the number of tasks in a Ansible playbook, or the number of modules, the number of parameters, lines of code, so on and so forth. The delta metrics are the differences between metrics between 2 successive releases. And so we created this subgroup of metrics, like project plus delta only, or total, and we analyze the performance. And surprisingly, here we have seen that the infrastructure as code metrics achieve the best results. And that's surprising, because usually in traditional application defect prediction, process metrics outperform product metrics. The third research questions is about the best predictor, so which metrics were selected most of the time for the best model. So we just used recursive feature elimination cross-validation using the random forest classifier, and we report the most occurring selected feature and combination thereof. Also here, we confirm the result from RQ2. There is an infrastructure as code metrics perform better than other kind of metrics. So as a takeaway, we created this main contribution, which is a machine learning based framework for infrastructure as code defect prediction, which is available online. And we noticed that, at least for the collected Ansible based projects, structural code metrics outperform process metrics. This was one of the major insights of this work. As I said, the framework is available open source on GitHub. Feel free to see and go and get back to me if you have any questions. And 104 defect prediction models already trained that can be used in practice or can be used for applications. And so you can find the full paper on IEEE Explorer, as well as the replication package on GitHub. Thank you.
Thank you so much, Stefano. Thank you. Okay, that was great. I'm told that we have to do questions at the end. Okay, does that make sense for everyone?
Yes.
Okay, thank you, George. So you can get started.
Is it okay? Do you see the slides?
Yeah.
Okay, great. So, hello everyone. I'm Aaron, and today I'm going to present you our paper towards incremental build of software configurations, which is a joint work with my PhD advisors, Jamel, Olivier, and Mathieu. And it has been published at the near track of IXC 2022. In this paper, we are considering highly configurable systems, such as the Linux kernel, with over 15,000 options that can be combined together to get configurations for different architectures. And building the kernel is really a crucial task, because it is the only way to get build failures from feature interaction, for instance, or getting build warning to find bugs. And there are hundreds of builds per day made by continuous integration infrastructure for the kernel, such as kernel CI, some tests from Intel 0 day, or predicting mode, or a need of a large amount of a data set on Linux binary for predicting models. And if building the kernel takes on average 10 minutes for an architecture like like x86, it will take a week of CPU time to build 1,000 of them. And smaller projects, as projects we use every day, such as terminal emulator, here we have Xterm. So we have 3 configurations of Xterm there. And the common practice is to build each one of them from scratch. Independently. And in this paper, we propose the incremental build point of view, which is building configurations one after another without cleaning the artifact in between, and letting the build system reuse the artifact the previous build. And for this case, for instance, we can gain 2 seconds in the small example. And so our vision of incremental build has 2 scenarios. So the first one is the ordering of configurations. For 3 configurations here, there are different order to incrementally build them. And here, for instance, we have an order where we can gain some build time for incremental build. And there could be another order where it takes as much as time as just clean builds, maybe because the configurations don't share any commonalities, and that's what we want to explore. We have a second scenario for huge configuration space, such as Linux, where first we take our previous order, then we want to generate configurations from basis configuration, such that the incremental build to these newly generated configurations is faster. And then, for instance, here we can build 8 configurations in 42 minutes instead of 3 configurations from scratch in 45 minutes. So we experimented on 2 highly configurable systems. The first one is x264 V2 encoder, and the second one is the Linux kernel. For the results of the ordering for x264, we generated 2 batches of 20 random configurations. And in the first batch, we could find an optimal ordering, but the gain was quite not that significant. However, for the second batch, we could find an order on which we could gain up to 11%. So this is the first insight on the fact that it is possible to find an optimal order to incrementally build configuration. For the Linux kernel, we couldn't find any order or outperforming clean builds for the random configurations we generated. However, we wrote a configuration generator that extracts dependency graph from the source code to generate configurations with slightly modification on the features, such that we can incrementally build them and reuse artifacts from previous configurations. And we can gain up to 66% of build time by doing so. So by having a clever way to guide the generation. So to sum up our paper, our contribution is bridging incremental build with software configurations. Then the insight of ordering, where we can gain up to 11% by finding the correct order to incrementally build this configuration set. Then the generation of configuration, finding a way to extract some knowledge from the project to have a smart way to guide the generation and save build time. And finally, as future work, we want to find an automatic way to detect the commonalities between configurations so that we can either order a set of configuration or generate them. I didn't talk about correctness of build systems, but we want to ensure that the binary produced by incremental build is correct compared to a clean build. And finally, we want to make important changes in the configuration space exploration while ensuring that it's faster for incremental build and still correct. Thanks for your attention.
Thank you very much. So next.
Hi, this is my turn, right? Hello, am I audible? Hello?
Rita?
Yeah, are you able to hear me now?
Okay, great. Can you share your screen?
I can hear you, yeah.
You can't hear me? Can anyone else hear me?
I was not able to hear for a while, but now I can. Yes.
Oops, sorry. Can anyone else hear me?
Yeah, Diego, but you're very low.
Okay. Okay, there you are.
Is my screen visible?
Yes. Go on. Someone else confirm?
Yeah.
Great.
So hi, I'm Dipanvita. I'm an undergraduate student at the International Institute of Information Technology, Hyderabad. And this is a work during my internship with IBM Research. So my mentors were Pooja Agarwal and Seema Ma'am from IBM Research India, and Rohan Arora and Bingzu from IBM Research Yorktown. So our paper is called Utilizing Persistence for Post-Factor Suppression of Invalid Anomalies in System Logs. So I'll first give a context of where anomaly detection comes in, which I think most of you would be knowing. So raw logs are extracted, first of all, from various microservices. And then these logs are templatized based on a fixed set of templates that we know. And the count of these templates, log templates, are obtained over time to ultimately give this template count vector. So this template count vector is eventually sent into the anomaly detector. So how anomaly detection usually works in this case is it tries to capture a normal trend in template counts, log template counts, and then it sees how much the values deviate from the normal template counts and regards the ones that deviate by a large amount as anomalies. So essentially the anomaly detector output is a binary label for every timestamp. So in this case, we consider time window. So it considers every time window, labels it as 1 or 0 based on whether it's anomalous or not. Now the problem with this approach is a lot of false positives come in, and if we are supposed to raise alerts for every one of these anomalous windows, then a lot of these alerts eventually don't evolve into a failure or a fault. So what we try to do is we try to reduce the number of false positives returned by the anomaly detector by defining something called persistent anomalies and just looking for windows that have persistent anomalies. So persistent anomalies, we define them as the ones that occur frequently, are dense, and also last for an extended period of time. So the dotted region on this diagram denotes the 3 steps in our process. So this works as a post-processing step on top of any anomaly detector like PC or autoencoder. So the first step is high frequency anomaly window detection. So what it does is the anomaly detector output, the label binary 0 or 1, is now iterated over in a sliding window fashion to get a time series. We then construct the moving average and moving standard deviation, and we identify peaks to see which windows have high frequency anomalies. Then in each window, we see if the number of anomalies occurring is greater than a certain threshold window density. If so, we regard them as dense anomalous regions. And finally, we merge successive or like neighboring dense regions to find any form of contiguous region, and we see if this duration is greater than a certain threshold level. So I'll explain this better through some experiments that we did. So SockShop is a simulated data set where we have tried for these two microservices in this particular figure. And we have HDFS, which is a real world data set. So the green line indicates the time series that is of anomaly counts returned by just the anomaly detector. And the orange line indicates the time series as per the SRE label. So the site reliability engineer has actually labeled a particular incident duration, and these regions are where the anomalies eventually evolve into faults or failures. So we see that there's a large number of false positives in the anomaly detector output, and we now go ahead and label each of these time windows as per our approach. So we see that stepwise we keep reducing the number of false positives till the final output, which is the yellow bars. And here we see that we have dropped almost all of these false positive zones, and we have only the regions of persistent anomalies returned finally. So to quantify this, we have two metrics: false positive reduction and true positive reduction. So FPR, or false positive reduction, is basically how much of suppression in terms of false positives we can do with respect to the anomaly detector output. And we naturally want a high value for this metric. And true positive reduction is how many true positives returned by the anomaly detector do we mistakenly consider as not persistent. So we see that for most of these services, we are able to reduce false positives by like 27%, 77%, and 28%, as against a very minimal reduction in true positive rate. In fact, the true positive reduction is in fact zero for a lot of the cases. So we are not affecting the performance of the anomaly detection, but we are trying to curb the number of false positives detected. So to sum up what we have discussed, so this is an unsupervised approach which identifies persistent anomalies, and it works on top of standard anomaly detection techniques. So its performance is based to a certain extent on the efficiency of the anomaly detection algorithm. So, but it is agnostic to all the models in the sense that it can be very easily extended, and we have at least a 27% reduction in the number of false positives that are returned by the anomaly detector for both real world and simulated data sets. Finally, there is also ample scope for a human in the loop feedback mechanism, especially for the peak detection part, which can make our algorithm adapt to changing workloads over time. That's about all I had to present. Thank you so much.
Thank you. Daniel, I think.
Yes, 1 second. There. Yeah, thank you. Oh, it has failed.
Sharing.
Yeah, I tried it. Got an error message. Now it should work.
There it is. There it is.
Okay.
Go.
Hello, everyone. This is Change is the Only Constant, Dynamic Updates for Workflows, which is joint work with Pascal Weisenburger and Guido Salvaneschi at the University of St. Gallen. So our work is about updating entire components in distributed systems. And such updates are important because you need them to fix security issues or to introduce features, for example. And such updates are more frequent or becoming more frequent. Modern DevOps organizations, for example, update their components, meanwhile, up to multiple times per day. But the problem with such updates is that they may break distributed transactions. And this is if you have only short running transactions or not that frequently running transactions, no big deal, because you can just repeat them and the required resources and introduced delays due to that are low. But this becomes problematic if you have quite long running transactions or on top of that, quite frequently running transactions. Because then you need huge amounts of additional resources to repeat these failed transactions, and you introduce huge delays, which might be too big for your application. And workflows are actually exactly in this corner. Workflows tend to be long running and frequently executed. And to solve this problem, we have safe dynamic software updating. And there the idea is in all these works to find out when it is safe to update a component in a distributed system so that none of the currently executing distributed transactions break, which basically means we don't break any transactions even though we update, and we don't need any additional resources or introduce delay for the update. So this is an example workflow. And you can imagine that for each execution of this workflow, a token is processed. So for example, this is now a workflow example execution. First, a hotel could be booked, then a car, and eventually a flight. And this example workflow here is distributed over two components. So parts of the tasks are running on the holiday component, and other parts of the tasks are running on the car rental component. And in safety SU, we now want to find out when we can safely update these components. And the state-of-the-art approach, or best state-of-the-art approach, is version consistency. And we see here in red, when it is according to version consistency, safe to update the car rental component, and in blue, when it would be safe to update the holiday component. And all currently running workflow executions must be within these safe intervals So the tokens must be in these boxes. So to give an example, if we want to update the car rental component with these two current workflow executions, it would be safe. But if we have this third one, which is outside the red boxes, it would not be safe. And in general, what we set out was to get more of these safe update intervals. We want to have more of that so that if we have an update, we can do it quicker. And when we do it, we have to introduce less delay into running workflows. And an idea we found, or something that we noticed, was that not every update actually changes something. There are many updates that don't really semantically change something. And in previous work by Kavrikov and Robillard, they called such updates non-essential changes. And they described non-essential changes as cosmetic in nature, behavior preserving, and that they don't give any further insight into the entities of the application. And simple examples could be just changing comments in a code or just renaming variables. Yeah. So where actually something changed and we have an update, but the semantics of the program didn't change. And with our safe dynamic updating approach, essential safety, we now want to leverage this distinction between essential updates, essential changes that actually have semantical changes, and non-essential changes. And for essential changes, we have the same safe update intervals as version consistency, as the state of the art. But for non-essential changes, where not much happens, we can also safely have these additional safe update intervals. We evaluated safe DSU in general on workflows and our work by simulating 106 realistic BPMN workflows. And through that evaluation, we found out that safe DSU in general is applicable to workflows, and that our approach, essential safety, can significantly reduce the overhead over the state of the art. And we also confirmed that, as we expected, the higher the share of non-essential changes is, the better is the performance of essential safety. A last aspect that we had to evaluate is our core assumption that in practice, indeed, many changes or many updates are non-essential changes. And to do that, we analyzed 8 monorepos, and we found out that there more than 60% of the component updates are non-essential changes, and practically probably even more than 90%. Yeah. So this showed us that indeed in practice, a lot of updates are non-essential changes, which allows us to use our improved, less overhead safety issue approach. To summarize our contributions, we applied previous safety issue approaches, which were only discussed for synchronous transactions, to asynchronous workflows. We introduced a better, less overhead approach with essential safety that leverages the distinction between essential and non-essential changes, and we evaluated all of that. Thanks for listening. All the details, of course, in our paper, a bit more detail than I could give now in these 5 minutes in the long version of this talk on YouTube. And we also have a full replication package on Zenodo, which you can use to reproduce and recover our work. Looking forward to your questions and the discussion. Thanks.
Thank you so much, Daniel. Thank you so much. So we have our last presentation now, and then we'll go on to questions. Thank you, Bram.
Okay, thank you. So hi, I'm Bram Adams, and I'll be presenting the work of my PhD student Dorian Olewiki in collaboration with Mathieu Nerol from Ubisoft La Forge. So you might know that about CI, and that CI is really essential in modern quality assurance. Basically, you have a commit, and then you have a whole machinery of CI pipelines that are triggered, and it will automatically do compilation and tests. And the idea is, if you have a test failure, or a compilation fail, or any fail during CI, there's a problem, there's a fault, and you have to do something. That's common knowledge. However, there are quite some situations where this assumption does not hold. So imagine the same situation as before. In some cases, some tests or even some compilation runs, if we just rerun them often enough, at some point they will actually succeed without changing anything, without changing the code, without changing the test, the build setup, anything. So that's quite weird. So you might think about the term flaky test. So flaky test is a subset of brown builds. A lot of build compilations fail just because some environment, hardware or software is not available, like a game console that goes off during a build and so on. And the problem is these brown builds, they're quite common. So we studied like 7 systems, 6 closed source ones, 1 open source one, which have variety and combination of programming language. And there we find that there's like a median of 13% of all failures during CI are actually brown. And 3 cases, actually, we have like at least 30 up to 58% of CI failures, compilation or test, or actually brown builds. And that's a problem because, of course, you can't just, like for every failure, keep on rerunning things. That takes a lot of time and resources. And developers start to really, no longer trust the CI and whatever it tells you. So for that reason, we came up with a language-independent approach to detect brown builds. Basically, we start from the build job logs. We extract features from that, textual ones that we put in TF-IDF. There's a lot of those features, so we try to do feature selection. We have some metrics as well about the build job and the commit. And then we have like an XGBoost-based model, 2 levels. All the details are in the paper. And the idea is that we'll classify a failure as saying a real failure or a brown build. And then we did large-scale empirical evaluation, where first we look at the accuracy of this approach. And there we found like a mean F1 score of 53% with peaks up to 84% F1. So this is like the result. So orange is our approach, blue is the baseline. So it turns out we'll give you 2 to 3 times better than the random baseline. And interesting as well, the best project in this case was also the one with the highest percentage of brown builds in its failures. But the project with the second highest percentage of brown builds in their failures was actually the second worst. So there's some correlation we found, but not perfect in that sense. We also compared to humans, actually experts. So we asked 6 build experts, take a look at 40 build jobs and classify them as a brown build or real failure. And again, orange is our approach, green, the experts. It varies. It's kind of similar. We're better sometimes, worse in other times. But of course, experts have to manually look at this for 3 minutes in some cases, so on average. So that's effort you can save with the model. And finally, we also want to see if you want to put this in production, like how often do you need to retrain the model? Do you need to do that every week, which could take take a lot of effort, or can you find heuristics to reduce that? So we came up with a bunch of heuristics, and with those heuristics, we were able to actually get similar performance as actually weekly retraining, so frequent retraining, but at a much lower retraining cost. In particular, so orange or our heuristics, it shows the best heuristic for a given project. Blue is the random baseline, so again, we're better than that one. Of course, we're mostly worse than actually the optimal heuristic, which always picks the best moment to retrain. So more interesting comparison is actually with weekly retraining, where we see that actually in most cases we're at least as good or slightly better in terms of F1 score, only one case slightly worse. But of course, the best thing here is that the model, the heuristic that we proposed, those models survive for like average of like 2 to 5 or even 6 weeks, which means in those 6 weeks, you don't need to retrain. You can reuse the same model, you can save a lot of resources. So to sum up, we proposed a language-independent brown build detection tool. We looked at performance, so it's as good as human experts. We also did some cross-project performance, which works sometimes depending on the project. And finally, retraining, so you can really speed up, like avoid having to retrain by a factor 2 to 6 with our heuristics. So thanks. I'm always interested in answering any questions.
Thank you, Bram, very much. Okay, so we'll start with our round of questions. Okay, let's start with the first project. If anyone has a question for Stefano.
So actually, I got a question for Stefano, if I may.
Right.
So interesting work, really like the thing. So I'm wondering, and it's interesting conclusion that your structural metrics seem to outperform the process metrics, whereas in traditional predictions like the other way around. So can you talk a bit about what happened there?
Well, I received a similar question this morning, so I'm really glad that also you asked. So that means that it's interesting indeed. Well, the fact is that no, no, good. So what happened is actually, and this is my assumption actually, because I think that in infrastructure as code and especially Ansible, I noticed less changes than application code. That's probably the reason. So we use around 46 structure metrics against 16 process metrics, well-known process metrics that are also implemented online in PyDriller, a well-known Python framework. But yeah, like when we measure the best predictor, the process metrics appear to be at rank 16 or 17. So before that would be a lot of structural code metrics. And I can't say what happened precisely, but my assumption is that the code wasn't changed so much as an application code. Also, the change was lower, and Ansible is mostly also declarative. So that's also a reason why you change less than procedural or imperative code. So,
Cool. Thank you.
yeah, thank you.
Anyone else, Paul? There.
Yes, a question for Bram. So you were saying that you go, what, 5 or 6 weeks before needing to retrain. Wouldn't number of builds be a more relevant metric for that?
So
How many
can
builds
you
are you? How many builds? Sorry. So if you're going 4 or 5, 6 weeks between builds, between retraining,
Yeah.
I would have thought that the number of builds between needing to retrain would be a more relevant metric. How many builds are you doing per week?
No, we didn't perform builds to the training. Yes, Diego?
Sorry, I think maybe Paul is asking Bram, or are you asking Stefano? Sorry.
No, sorry, I'm asking Bram.
Okay.
Yeah. Sorry, Stefano. I have a question for Stefano later, but go on. Maybe we can do this like this. So
yeah. So thanks for the question. So we do. So the approach depends on two sources of data. So we have build log related data, but then we also have these metrics about the actual build, and some of them actually go in the direction you were suggesting in your question. So for example, we have for a given build, like how many times have the build been run since the last so like how many commits since the last rerun for this build job, for example, or like, and how many commits, how many builds since the last time a file like that was touched. So we have some information in that direction. And if you look at the most like meaningful or important metrics, somehow the textual ones seem to be a bit more influential in the systems we looked at. But then again, there is this signal definitely in those commits you were, those metrics you were suggesting. Yeah, thank you.
Okay.
Thank you. So I have a question for Stefano. If no one else wants to ask him another question. Okay, so I'll go ahead with my question. First, I'd like to build on what Bram brought up. I think that it's very interesting too, and I would add I've been a user of Ansible for many years, so from my industry perspective, I'd add that Ansible is a tough tool from the structural point of view. So maybe that also so brings a bias in that direction. It's not so easy, and complexity grows a lot when you go from the structural point of view when you grow your Ansible code. So it's not so easy. And I also would like to add, maybe if it helps, is that what you find is that sort of reusable configurations that have been tested very widely, everywhere, but by many people. So those are very good at running in many places. But when you do create your own, you get a lot more problems, So your own, the little tasks that you create using other tasks to do what you want to do, you get a lot more trouble from them that you get from very, very standardized, mostly generic tools built by others. So there's a difference there, and I this rings with the structural issues that you found in your research. So that resonates a lot with me. So
Good, very good to know. I mean, may I add something if I have a couple of minutes? I would like to add a comment to an answer that I gave to Daniel's questions this morning. So, Daniel, if you're here, I would like to discuss with you. So, he asked me if I would expect, correct me if I'm wrong, the same result on other configuration tools, language, or other infrastructure provisioning like Terraform. And I said, yeah, for sure, I will expect the same things. Now I would like to reframe a little bit my answer because I get a little bit of documentation during the day. I was looking specifically at Terraform, and I would like to know also Diego's opinion on that. And I noticed that one of the main differences between Terraform and Ansible, for example, is that Terraform depends a lot on the lifestyle management, while Ansible doesn't rely at all, let's say, so on lifestyle. It doesn't have a life cycle management. It's just a procedure of tasks that are executed and so on and so forth. So I think that, of course, the result may be similar in general, because if a human can spot the error, I don't see why the machine learner with proper data can spot the errors. The fact is that we are adding a further level of difficulty, which is about understanding and keeping track of the state of the infrastructure, because Ansible, Terraform tried to ensure that the desired state is always satisfied for the environment. So that's the main thing, I guess. And it's also nice to know that we are trying to do a similar study on Tosca, and we already found that the similar metrics that I use for Ansible are also good for Tosca. So we might ask, so why Tosca is not similar to Terraform, why we can have the same performance? And in that case, I guess the Tosca is just based on Ansible on YAM as Ansible is. So perhaps the fact that they are based on the same language allows to use similar structural code metrics that achieve similar performance, while for Terraform we have to think about other metrics for training.
Yeah, great. Thanks for going into more detail on the question I had this morning. I really appreciate it. So basically, what you also see as a core difference, which is challenging, is that even though Ansible is declarative in its shape, it still has these imperative tasks, which you don't have in Terraform, which are hidden there in the providers, but you don't have them on the user side anymore. Yeah.
Exactly.
Great. Yeah, thank you. Yeah, thank you both. Yeah, I think it's very enlightening. Okay, great. So we'll move to the next presentation, okay, towards incremental view build of software configurations, okay? Thank you, Daniel, too. So questions there? Or comments? They don't have to be questions. Maybe you can add something or share your perspective.
So
on the presentation.
I've got a comment, perhaps. So because I like the work because it's quite ambitious. It's quite a big challenge to do. Like there's so many different variants. All of them are valid, but this is a huge search space. And I think maybe so the direction you mentioned are quite interesting. You already have some results as well. I remember like. It's a later problem, but different. Like a while ago, I think it was XC 2014. There was this work about basically in a system with plugins where you can have all these combinations of plugins configured to test them. And there was this, I think it was Tien Nguyen's lab who made this approach, Varex, I think, which basically just ran the tests once, but in every test somehow like there's like a different execution in parallel for different combinations of plugins which have like similar or different kind of behavior. So I was wondering maybe that kind of idea could actually be applied to your case, where basically you just like the idea, okay, one build, but during the build we notice, oops, either we do this or we do that across the different configurations, that you just do them in parallel and something like that was just something that crossed my mind. So it's like basically the world of variability aware testing, basically.
Yeah. I mean, that's the key word. Okay, so thanks for the reference. I think I don't have anything to add about it because it's quite related and really relevant. So thank you. Thanks.
Yeah, I'll send you the link and
are muted. Diego, you are mute.
Sorry. Yeah. Thank you, Valeria. Thank you so much. Yes.
You're welcome.
Great. Had to happen. My question was, how do you detect incorrect configurations? Okay, when you did the changes, when you do the optimizations there, is it very obvious, or is there some?
So there are
room
two
to,
ways. The first pragmatic one is that when it doesn't build, it means that the configuration is incorrect. So that's the first one. And the correctness I was mentioning in the talk was, for a build to be correct, first we need that the binary that is produced by a clean build, so the classic build, must be the same as the one produced by an incremental build. So we say that an incremental build is correct when it's consistent.
Right. That's great. Yeah, that's a great approach. Yeah. Okay. Perfect. Yeah, it sounds fantastic. Okay, great. And one more thing, when you generate alternative configurations, right? You said about 200. What are the inputs there? What are the how do you get to those modifications, right? What?
Okay. So what we do is we build because, for instance, in Linux we have the configuration options that we combine in a configuration file, so that makes the configuration. And these options have dependency, but this dependency are too abstract for the build system. So what we needed is a dependency graph between the files of the different options. And then when you have a dependency graph, you just check for a configuration. If I modify one option, what is the impact at the build system level? And then we take some candidates which have a less impact on the dependency graph, and then we add it to the configuration, and then we incrementally build from the first one to the newly generated configuration. And that's how we do it.
Okay, thank you so much. Thank you. Okay, if no one else has a question for Georges, we'll move to the next. I see in the chat we have some questions. Thank you, Bram. So we move to the next one. Sorry if I'm maybe I'm not allowing full Any questions for Divan Wita on the persistent anomalies presentation? Well, I have a question. Oh, Bram, thank you so much.
Yeah, I was just wondering the anomalies that are supported by the approach. Like, is it a specific subset of anomalies, or is it quite wide open?
So we have a fixed set of templates, around 1,000 templates that we considered, and our approach mainly looks at quantitative differences based on how much the anomaly template counts, the log template counts vary from their normal values. So we have trained the anomaly detectors to capture the normal behavior of the system, and the anomalies are in terms of how much if new templates are occurring which were not occurring before in the normal behavior, or they're occurring with a higher frequency or lower frequency than expected.
Okay. And so those templates that you define, or these are kind of existing catalog of templates, or?
Right. So the templates we used IBM AIOps, which is a standard pipeline. So we refer to the standard set of templates that are followed for these particular services. So for SockShop, we had a set of different templates, and for HDFS, we had a set of different templates. So the pre-processing was done using the AIOps tool itself, and we worked as a post-processing step on top of the anomaly detector after that.
Okay, good. Thank you. You're muted again, Diego.
I used to be muted. I like to talk all the time. No, it's not true. Yeah, that is true. Okay, sorry. No, my question was whether the advantages here are beyond, or you see advantages into your approach beyond the excluding the false positives, the false negatives. Sorry, you highlighted that aspect, but I was thinking more about more emergent problems, right? Widespread problems that are not easily detected by standard monitoring tools, right? Something is not unavailable, but at the same time, it's a little delays causing problems somewhere else, right? So you see it as a problem, but at the same time, you're not finding it somewhere else. Is that something that your approach could bring, or am I misreading the contribution?
So yeah, one thing that was also brought up in the morning in one of the discussions was so a lot of these incidents when they are labeled from the start and the end is usually based on user reports, and then an SRE comes and verifies it. So what we can do using our approach is we can actually precisely pinpoint the point of time where these anomaly counts started uh, increasing, where these log template counts started increasing or decreasing. So that can help pinpoint the exact time where an incident started, so that more proactive actions can be taken. And the other thing is we also tried after the paper this approach on metric values, just raw metric values like network traffic and something features like that. And we saw that even without anomaly detectors, because our approach is a time series based approach, and we can always sliding window over the values that we get. So we can actually also identify faults just by doing a time series approach and peak detection, the approach that we're following, even without going into anomaly detection. So that can bypass the whole anomaly detection pipeline and can directly give you, say, where faults are occurring and which services they're occurring in.
So if there are no more questions for the Manguita, we can move to changes the only constant. Thank you. Thank you, Daniel. Coming back. So not sure. Okay, yeah. So the questions on the chat or for Bram. So for Daniel, anyone has a question or a comment or something that you'd like to contribute?
Just one thing. At the end of your talk, Daniel, you mentioned like a bit casually, like did a study of 8 monorepos, and you found the percentage of. But that seemed like a big study, actually. Can you elaborate a bit more about that study?
Yeah, so it's not a too big study. So what we did there, we took these monorepos, which were open source repos on GitHub with between 10 and 40 components.
Mhm.
And what we noticed, or an assumption that we took for that study, is that every commit produces an update. And then we took some of these trivial techniques to figure out whether an update may be non-essential or not. In particular, we just looked at do the files change of a component. And we saw, and I mean, that's also something you would intuitively, I guess, assume if you have a monorepo and produce updates for every commit, most components aren't affected of a commit. And that's basically what we actually empirically found out in that monorepo study and what we actually did. And that's also why we say, like, conservatively, we have this 16% with slightly changed assumptions, we already have 90%. But in practice, if you have more precise methods, so actually would start analyzing the semantics of the program, so not only whether files change or not, you might even get higher percentages than we now have as a conservative approximation.
Cool. Okay, great. Thanks for clarification.
Great.
Yeah. Good question. Thank you very much.
Thank you, Bram. So I have a question for you, Daniel. Do you think that I'm thinking about this in terms of maybe a continuous delivery setup, right? Where each commit, as you said right before, might be an interesting update. So again, making that flow better is a great asset, right? A great result for the team and for the business. So I was thinking, would it make sense at some point that the team tag a change in terms of essential or non-essential, or components affected, maybe hint at this to improve the performance of the process? Or maybe that's not something that, does that make sense to you or not?
Yeah, completely. So definitely, I think that's really something that in practice, when one takes these methods now and applies them to practice, that's something that should be truly considered. So ideally, I think you want to have something that you have a system that also then gives a comment on how true is what the developer thinks, whether the update is essential or non-essential, to give more certainty. But I think generally you can get more precision if you also take the developer opinion into account and not only conservative static analysis. So I definitely think it would be a good idea, and it should be also fairly easy for developers to say, is this
Exactly.
commit actually changing something,
Right,
or
exactly.
is it just a cosmetic
Yes,
thing that should
yes,
preserve the semantics of the program?
exactly. Because I think the semantics part is what spawned this perspective, right? And at the same time, this idea that it's a business decision too, right? You're saying we want this update out there, right, as soon as we can. So there's someone there making a decision, right? Even in continuous delivery. So I think it's interesting too. And I find what you brought up, this idea that you get feedback from that. So developers get feedback saying, hey, you thought this was non-essential, but it was essential. So this brought up a problem, so you can learn, and next time you tag it, you're going to be better. So everyone's learning. So I think that's a great, two ways improvement outcome.
I mean,
So sounds great.
it's
Yeah,
always also a discussion. How do you want to have the strict safety guarantee? Then you would
exactly,
need to guard the developer a lot, but still it
exactly.
might be helpful if you have ties, or if you can
Yeah,
make your analysis more precise by the developer input. But if you say, like, yeah, we want to be better than having none of these, but we don't need 100% safety,
exactly.
then you can give this developer input more power
Exactly.
already
And
too.
that might be domain dependent, right? As I think Bram
Yeah.
brought it up before we started. So yeah, that's very interesting. Thank you so much, Daniel. So we'll go back again to Bram. Thank you, everyone. So we have time for one more question, I think, or two more questions for Bram, if anyone has them. Thank you. So I have a question. I think Valeria had a question and you answered that on the chat, right?
Yeah,
Thank you so
actually,
much.
well, so for
Go
that
ahead.
thing,
Yes.
so oh yeah, Valerie, yeah, because we were talking before the thing about flaky tests. So brown builds are actually like a superset of that, in the sense that there could all be flakiness, so to speak, because of compilation. Like during the compilation, there's a missing dependency, a game console that is used to compile or run some stuff. It isn't like accessible, and it's especially important in video game industry because you don't just have source code and a bit of data. You also have artists, like creations. You have AI. Kind of models, you have kind of physics engines, you have all these kind of things with their own tools. They're not code, but they could also be flaky, or like, so to speak, and that's
Okay.
actually what brown
But in
builds.
some cases, there is no differences between flaky tests and brown bills, if I understand it correctly.
Yeah, so
Right.
if you have a flaky
Okay.
test, by definition, you have a brown build. But if you
Exactly.
have a
Okay.
brown build, it's not necessarily a flaky test. That's a bit the
Exactly.
thing.
Okay.
It's,
So you
Thank
have
you.
other failure. Thank you, Valeria. Thank you,
yeah,
Bram.
great question. Thank you.
Okay. Yeah, great question. So I had a question for Bram. I think it was, I think the research is great, and I think you're pointing up at a big issue for us developers. I'm speaking as both, right? We suffer a lot because, as you said, the time it takes to diagnose and decide whether a build is a brown or is a red, really. So it's a really, really stressful time and takes a lot of work. So I find that the results are very, very good. Um, I think, as you brought up, that accuracy was similar between the automatic detection and the expert detection. So I think that's very
Mhm.
important because that points at improving the life of the developers doing the work, right? Because they
Yeah.
don't need to, they can rely on the system. So my question was whether the retraining was very hard to set up and stuff where there was a lot of work from the end user point of view to configure or check, or maybe that's something that's highly automated, and you don't have to do anything more than provide the resources.
Yeah, it's highly automated. You just need to select the best heuristics for when to retrain, and of course access to the build log. But otherwise, it's automated. It's more the interpretation afterwards. Like
Right.
if you say,